Okay, so now we'll start with this module on Bayes classifier. So this is very much a probability-based approach. So let us go through some fundamentals about probability, conditional probability, and so on. So to begin with, probability of an event is the likelihood for that event to happen. So for example, if I say the probability of rain today is 0.4, it means in a scale of 0 to 100, there's a 40% chance for a rain today. And probability typically is represented in a scale of 0 to 1. So 0 means not at all possible, and 1 means 100% possible. So 0.4 is a scale of 0 to 1, gives you an idea how likely the event could happen. So that's about this probability as it is. Now, there's something called conditional probability that's typically represented like this. Probability of event A to happen, given that event B has already happened. So given that B has happened, what is the probability that A could happen? That's different from what's the probability that A could happen just as it is. So here, given that B has happened, what's the probability A will happen? So it's different from just probability of A or probability of B. Now there's a formula to determine a compute probability of A given to B. That's how it is called. It is probability of B given A times probability of A. So this denominator or the one B given A, you have that times probability of A divided by this probability of B. So if the individual probability of event B is not given, and if A and B are the only two events that are considered in the system, then probability of B could be computed with a formula like this. Again, A and B are the only two events in the system. So that is probability of B given that A has happened, and for A to happen, there's a probability of A. Then plus probability of B given that A has not happened times probability that A will not happen. So you consider B to happen given that A has happened, or B to happen given that A has not happened. And for each of this, you multiply by corresponding probability for A to happen or A to not happen. Okay, and we'll make use of all these things and see an example. So consider a lab that has been testing patient for COVID with one of the two possible results of a lab test, either a positive result or negative result. And the lab guarantees that the results are 99% accurate. That means if we have the disease, let me make it big. If we have the disease, the result will be positive in 99 of 100 tests done. And if you don't have the disease, the result will be negative in 99 of the 100 tests done. So if you don't have the disease, the result should come out as negative. If you have the disease, it should come out as positive. And let 3% of the population actually have COVID. Then if the test taken for a person, let me make sure I'm sharing the screen. Gives a positive result, what is the probability the person has COVID? So somebody goes to a lab and takes a test for COVID and the result comes out as positive. Then what's the probability the person has COVID? Because there's only a 99% accuracy of the test. It's not 100% accurate. So if the test result comes out as positive, doesn't mean the person really has COVID. There's still a probability the person may not have COVID. Because again, only 3% of the population actually has COVID, not 100% of the population has COVID. So that's the condition there. Okay, so what we want to determine here is probability that a person has COVID, given that the test result is positive. So the test result has come out as positive. What's the probability that the person has COVID? So according to this formula here, A is the person having COVID and B is the test result is positive. So you can use that formula here. So this is A and this is B. So we know that probability of A given B is probability of B given A times probability of A divided by, so the whole thing divided by probability of B. So we don't know. So what is something we know here is there is 3% of the population actually has COVID. So probability of a person to have COVID is 0.03. But probability that test result is positive is not given right away. So what we have to do is compute that using this formula that we saw at the end of the previous slide. So probability of test result, that is B in this case. Okay. So probability of test result is positive equals probability of the test result is positive given that person has COVID, which is A, times probability person has COVID. That's one case, plus probability of test result is positive given that the person does not have COVID. And this times probability person does not have COVID. Okay, so the test result is positive. What's the probability of that to happen? So the test result is positive given that a person has COVID times probability someone has COVID. Test result is positive given that someone does not have COVID times probability that someone does not have COVID. Okay, so now if someone has COVID, the test result is positive in 99% of the 100 cases. That's the accuracy of the lab test. So that's something given to us. So this term, if someone has COVID, the probability the test result is positive, that's accuracy term 0.99 times probability someone has COVID is 0.03 plus if the person does not have COVID, what's the probability the test result is positive? If a person does not have COVID, the result should be negative. And that will happen 99% of the time, 0.99. Then so to come out to be negative, it will be 0.99. So to come out to be positive, it will be 1 minus 0.99. Not to come positive. It should have come negative with a probability 0.99, but it has come, test result is positive. So that probability for that is 1 minus 0.99 times probability the person does not have COVID. There's going to be 1 minus of this 0.03 because probability someone has COVID is 0.03. So probability that someone does not have COVID is 1 minus 0.03. So if you compute the value for this, zero point 0.0394 is the probability the test result is going to be positive. So we got all of the terms that we want here. So probability someone has COVID, given the test result is positive, there's probability the test result is positive, given that a person has COVID, times probability person has COVID. So we can notice that this is actually the first term in this formula here. Then the whole thing divided by probability the person, but probability the test result is positive. And that's what we computed just now. So if you plug in all these things, it's going to be 0.99 is the accuracy term. Probability if someone has COVID, the test result is positive, times the probability someone has COVID is 0.03. The whole thing divided by probability test result is positive. That's going to be 0.0394. So if you do the math for this, so 0.7538. So that means if the test result comes out to be positive, the probability a person will have COVID is 0.7538. It's not 1, because only 3% of the population has COVID, and the test result can be accurate only 99% of the time. So given all these conditions, the probability that if the test result is positive, someone has COVID is 0.7538. Okay. So again, we'll start looking at from this module the classification algorithms, starting to build the actual model one way or the other. So for this classification problems, you're given a training data set, and it will comprise of features and values for these features, could be either categorical or numerical. And then the class of the record could be either a simple yes or no or 0, 1, which is called binary classification problem, or it could be like more than two classes. Class 0, 1, 2, 3, if you want to represent the classes numerically, or like in the case of species, iris, data set, you have the name of the flowers as a class. So it depends on the problem and the data set. So the goal of a classification algorithm is to basically build a model based on the training data set and then use that model to predict the class for the test data. And so we will start with name-based classifier in this module. And it is very much suitable for both binary and multi-class classification. Some of the other classification algorithms you're going to see are designed primarily for binary classification. So if you want to use them for multi-class classification, we have to kind of tweak them and modify, or run it multiple times to be able to do multi-class prediction. So on the other hand, naive-based classifier is kind of inbuilt. Just straightforward is can be applied for both binary and multi-class classification. And it's scalable and very fast, and it can be easily trained on very small data sets. So the larger the data set, again, the more difficulty it is to train this more classifier. Now, one main assumption of naive-based classifier model is, or algorithm is, the features are assumed to be independent. And we will come to that this particular assumption when we look at some examples why this is kind of built in to the model, to the classifier. It assumes that the features are independent. Okay, so it doesn't mean that it will not work if the features are not independent, but the accuracy or the validity may not be 100% possible in those cases. And it is also more suitable if the features take categorical values rather than numerical values. So it's more suitable for classifying data sets for which the features have categorical values. It's straightforward again in those cases. Whereas if the features have numerical values, we have to go with multiple iterations, and look at an example later in this module, and then choose or build a classifier. So the first classifier we saw is the K nearest neighbors algorithm. It's the other way around. It's more suitable for numerical data compared to categorical data, whereas with Bayes, it's more suitable for categorical data compared to numerical data. So again, notation wise, this is what we'll use. So the features are represented as x1, x2, x3, and x4, and with the feature identifiers written like this below. And then the record numbers, or like x1, x2, x3, with the record numbers indicated above. And y is the class of the record. So it's very much based on the conditional probability formula we saw earlier. So given, for example, a test record x of t with feature values xt1, xt2, and up to xtm. So we have m features. What's the probability that this test record will belong to a class k? So y equals k. So if you again remember the formula, it is probability of A given B is probability of B given A times probability of A divided by probability of B. So A here is the test record and B here is the class. So we can say probability of, given a test record B, the class y equals k, is the other way around. Given that the class y equals k, what's the probability for this test record to be observed times probability of the class k divided by probability of the test record again to be observed without any condition. Okay, so now if you put it here, that means probability of xt equals xt1, xt2. Again, these are the feature values for different features x1, x2 up to xm, given that y equals k. Now, since the features are assumed to be independent, we can break this into multiple terms like this. That means given that y equals k, what is the probability for x1 to the feature x1 basically to take the value of xt1 that we observed for this test record times. Again, independent probability is basically this. So if you have, say, events I, j, k, so what is the probability that I, j, k appear or occur together? If I, j, k are independent, then you can say it's probability of I times probability of j times probability of k. So if the three events here, I, j, k, the three events are independent of each other, then the probability that all the three of them can occur together is equal to the product of the probabilities, probability of I times probability of j and probability of times probability of k, the product of the probabilities. The same thing here. Since the features are assumed to be independent, the probability that we can observe a feature value xt1 for x1 and xt2 for x2 and so on, xtm for xm, is going to be the product of all these probabilities from x1, starting from x1 to xm. So if you look at the product of the probabilities, it will be like, given that y equals k, probability of x1 equals xt1 times, given y equals k, x2 equals xt2 times, given y equals k, x2 equals x3, and so on, up to xm equals xtm. So that's the first term. This B given A broken down, and then times probability that we observe a class y equal to k. So among all the classes, among all the records, basically, how many or what fraction of the records have class y equals k? That's what it is. Now divided by probability of B, which is again probability of xt, a text record will have all these combinations of feature values to occur together, xt1, xt2, and so on. And this, since again the features were independent, we can break it down into probability of x1 equals xt1 times probability of x2 equals xt2 times probability of x3 equals xt3 and so on up to probability of xm equals xtm. Okay, so let us look at a simple example to begin with, and then we'll slowly increase the complexity. So here we have COVID data set again with 4 features. Sore throat and cough is one feature, runny nose is another, fever is another, difficulty in breathing is another. And the class is yes or no, whether the person has COVID or not. And each of these have their own values. So again, the features could have more than 2 values. Here, each feature has the first 3 have only 2 values, and whereas difficult in breathing have 3 values: mild, no, and strong. So we can use Excel to kind of key in this data set and make it easy to go through the calculations and actually have them here typed in. So I'll explain that now. Um, okay. So what we need is to basically build a table of the absolute probabilities and conditional probabilities. Okay, so let us start with sore throat. I'm going to make a copy of this. The sore throat and cough. Okay. So this feature has 2 values, yes or no. So let's type down those values, yes or no. And if you want to first find out what is the unconditional probability for the sore throat and cough feature to take the S value, similarly the no value. So you can sort it based on the sore throat and cough, and then by the COVID-19, the class. So basically you can see there are totally 8 records, and 4 of the 8 records take the value of S for sore throat and cough, and then 4 of them have no. So that's independent of any other feature of the class. Just based on this feature, you have 4 S and 4 no. That's unconditional probability. So you can say that's the absolute probability, you can call it. So that's going to be 4 divided by 8. Out of the 8 records, 4 have S for sore throat, and 4 divided by 8 no for sore throat. Then we can come up with the conditional probabilities as well. So for that, we have to look at the class of the record. So the record again can be of either class yes or no. And so here looking at for sore throat being equal to S, how many of the records have yes? That's a class. So there are 4 records that have S for sore throat. Out of these 4 records, how many have an S for the class? And here you notice 3 of the 4 have an S for the class. That means given that someone has sore throat and cough equals S, what's the probability that COVID-19 equals S? That's what it means. So that's 3 over 4. Likewise, given that someone has sore throat and cough, which is S, what's the probability that COVID-19 equals no? That means that will be 1 of the 4 cases have no in the test record. Likewise, there are 4 records that have no for sore throat, and out of this, 2 have an S for the class and 2 have a no. So 2 out of 4 is S and 2 out of 4 is a no. So that's how we build the conditional probabilities and absolute probabilities table. So here in the slide, you can see I have I've done that for all the 4 features. And I also indicated here how you get those numbers. Okay, so let us do now for runny nose. Let's save this. We'll do now for runny nose. And runny nose again can have either yes or no as its feature values. So we sort this table based on runny nose and then by COVID-19. So we observe 5 of the 8 records to be yes for runny nose and 3 of them is no. So you can say 5 divided by 8 is absolute probability. And then 3 divided by 8 is absolute probability for runny nose to be no. Then for the conditional probabilities, out of these 5 cases where runny nose equals S, 3 of them have COVID-19 equals S and 2 of them have no. So it's going to be 3 over 5 for S and 2 over 5 for no. Then out of the 3 records where runny nose equals no, we have here 2 of them as yes for class and 1 is no. So 2 out of the 3 is an S class and 1 out of 3 will be a no class. Okay, so that's how we get these numbers. So this is like actually building the model in the case of naive Bayes, because then when we have a test data, we're going to actually plug in the numbers, pick up the numbers from these tables. So let's do now for the next feature, which is fever. Again, the values for fever are either yes or no. So the absolute numbers, so let us sort the table based on fever. Again, the sorting is just for easiness for us to count the number of occurrences of the records with these values as no, like that. So again, for fever, we have 5 of the 8 records to have S as a value and 3 of them have no. So the absolute probability will be 5 over 8 and 3 over 8. Then for the conditional probabilities, among these 5 that have S for the fever, all the 5 records also have S for the class. So it's going to be like 5 over 5, which is 1, and 0 over 5 for no. Now, out of the 3 records that have no for fever, we have also a no for COVID-19. So that means 3 of the 3 have a no, and 0 of the 3 have an S. And the last feature is difficulty in breathing. And there are 3 feature values here, which are mild, no, and strong. Let's do it. It doesn't matter, but let's do it. It could be no, mild, or strong. So there's an order here. And we'll just count the number of records that have these feature values for difficulty in breathing. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . So there are 2 mild cases, 3 no, and 3 strong. So 3 no, 2 mild, and 3 strong. And the absolute probabilities are going to be this 3 divided by 8. So 3 of the 8 cases or records overall have no as the value for difficulty in breathing, then 2 over 8, then 3 over 8. So now the conditional probabilities, out of those 3 records that have no for difficulty in breathing, how many have S for COVID? None of them. All the 3 are no. So that means this is going to be 3 over 3, and this is 0 over 3. Out of the 2 mild cases, both have S for COVID. So that's going to be 2 over 2, and this is going to be 0 over 2. Out of the strong cases, all the 3 strong cases have S for COVID. So that's going to be 3 over 3 equals 0 over 3. So this is how we build the conditional probabilities table, again along with absolute probabilities. So now if you want to run it through a test case, which is this, again I represent this which is as x1, x2, x3, x4. So x1 is sore throat and cough equals no. So given this test record, actually, we want to find the probability that it belongs. What is the probability a person has COVID, and what's the probability a person does not have COVID, and pick the larger of the 2 probabilities. So this can be worked out like this. So given this test case, what's the probability someone has COVID? That's what we want to find. So that's equal to probability of, given the person has COVID, what's the probability for the test case to be observed, times probability of the person has COVID divided by probability of the test case. Now the test case is actually the combination of these 4 feature values. So probability of, so that's equal to probability of x1 equals no, comma, or x2 equals no, x3 equals yes, and x4 equals strong, given these combination of feature values, given that the person has COVID. Times the probability the person has COVID divided by, again, the probability of these 4 feature values to be observed without any condition whether the person has COVID or not. Okay. So now now is the time the independence of the features is made use of. So given the person has COVID, that means the class equals S. What's the probability for x1 equals no? So in our table, we look at these entries now. Looking at x1, which is sore throat. So the person has COVID is S class, and x1 equals no is this. So we're looking at this feature value no, and the person has COVID, S class. And the number we have there for the probability is 0.5. That means if a person has COVID, given that the person has COVID, what's the probability that sore throat and cough equals no? X1 equals no is 0.5. So that's the number. Then similarly, person has COVID, so S class for all the four features, but feature value is no. So X2, which is runny nose, the feature value is no, and class is S. So 0.6667 is the probability that given the class is S, the running nose feature value is no. So this is our X1, this is X2, this is X3, and this is X4. 0.667. Then again, class is S, X3 equals S. So class is S, X3 equals S as well. So the probability is 1. The conditional probability is 1. Then X4 is strong. The class is S. So class is S, X4 is strong. So 1 is again the answer for the conditional probability. Times the person has COVID. So for that, go to the test record. Among all the 8 records, 5 of them have S for the COVID-19 class. So that's why it's going to be 5 over 8 is the probability that the person has COVID in this data set. Then the absolute probabilities. So x1 equals no, x2 equals no, x3 equals this, and x4 equals stop. Again, remember the features were independent according to assumption. So we can break it down into probability of x1 equals no times probability of x2 equals no times probability of x3 equals s times probability of x4 equals strong. That's what we're going to do here. So we're going back to our tables. So you see here, the tables are like our model here, and you're going to actually pick up the probability values from the table appropriately. So x1 equals no. x1 is our sore throat, and the no case feature. 0.5 is the absolute probability. So among the 8 records, 4 have sore throat and cough as no. X2 equals no, and the absolute probability is 0.375. X3 equals yes. The absolute probability is 0.625. Then X4 equals strong. The probability is going to be 0.375. So that's the unconditional absolute probabilities. So if you simplify the math here, you get the final answer. So it's 4.741. Now remember, we saw the probabilities, absolute probabilities or the unconditional probabilities have to be less than or equal to 1, whereas conditional probabilities could be greater than 1, like we see here. So what we found here is, given a test case, what's the probability the person has COVID? Now, we don't know, given that particular test case again, what's the probability the person does not have COVID? You have to find it out and compare the two numbers, and whichever is stronger, we'll go with that number. So So given that test case, what's the probability the person does not have COVID? Is given the person does not have COVID, what's the probability the test case is observed? times the probability the person does not have COVID divided by the test case, probability of the test case. So in this case, so the test case is still the same. So like this. So now the probability the person does not have COVID. So the class is no here. So you have to go back to the unconditional probability, so the conditional probabilities table and pick up the numbers for now the class being no. So the class is no. What is the probability for, so the class is no. What's the probability for x1 equals no as well? That's what we are having here. For the class to be no, the person does not have COVID, what the probability of x1 to be equal to no? And that's given here as 0.5. Class no, x1 equals no as well. Then class no, x2 equals no as well. So class no and x2 equals no as well. So it's going to be 0.333. And class no, x3 equals s. So class no, x3 equals s is going to be actually 0 for class no, x3 equals s times x4 equals strong, and class no is also 0 times probability of class no to be observed. That's going to be 3 of the 8 records have no as the class. Then the absolute probabilities, which is same as what we had earlier, because the test case did not change. So you can copy from here. So if we do the math, it's going to be 0 here because we have at least 1 0 in the numerator. So it's going to be 0. So that means given the test case, which is a combination of these 4 feature values, what's the probability that person does not have COVID is actually 0. So the probability the person has COVID is actually larger, greater than 0. So the final answer is the person has COVID or predicted to have COVID. Okay. So let me stop with this, or let me just take a pause and let me pause this. Yes. Okay, so let us continue. So look at the second example. So this is the weather data where we have actual cases of someone whether played tennis or not, yes or no, or the two classes, based on these 4 feature values: outlook, temperature, humidity, and windy. So outlook has rainy, overcast, and sunny as the 3 feature values. Temperature has hot, mild, and cool as the 3 feature values. Humidity has high and normal, and windy has false or true. So as usual, the first step is to build the absolute probability and conditional probability tables. And I have already typed the weather data here, so I'm going to just copy and paste it. So Plate thickness is a table name. So finding the conditional probabilities is actually what we're building a model as well as absolute probabilities. So we'll do first for Outlook. So we'll copy the record, the table here, and sort them based on features. We'll sort it based on Outlook as well as then by the play tennis class, yes or no. So that way, for each value of Outlook, it will sort yes or no like that. So that's more convenient for us to visualize. Okay. So for Outlook, the possible values are overcast, rainy, and sunny. And the numbers are like 4 overcast, 5 rainy, and 5 sunny. So 4 overcast, 5 rainy, and 5 sunny. So the absolute probabilities are going to be 4 over 14 because there are totally 14 records. Out of the 14 records, 4 have Outlook as overcast. So this is the probability that Outlook equals overcast. Then probability that Outlook equals rainy among the 14 records is going to be 5 over 14. So 5 of the 14 records have Outlook as rainy. Similarly, 5 of the 14 records have Outlook as sunny. Okay, so that's absolute probabilities. So now we have to find the conditional probabilities. Depending on the classes, so we have yes or no as the possible 2 classes. So among the 4 overcast records, all the 4 have S as a class. So that's going to be 4 out of the 4 have S as a class, and 0 out of the 4 have no as the class. Okay. Then out of the 5 rainy records, we have 3 no's and 2 S. So we have 3 no's, 3 out of the 5 have no, and 2 of the 5 have S. And out of the 5 sunny records, you have 2 no's and 3 S. So you have 2 no's and 3 yes out of the 5 sunny records. So that's how you find the conditional probabilities. That's for Outlook. So now let's do for temperature. Temperature feature values are, you can sort based on temperature and make sure you capture all the feature values. And then sort by plate tennis. So cool, hot, and mild are the feature values. So cool, hot, and mild. And then you have 4 cool, 4 hot, and 6 mild. So 4 cool, 4 hot, and 6 mild. Now we are ready to calculate the absolute and conditional probabilities. So 4 over 14 is the absolute probability for temperature to take the value of cool, irrespective of any condition. Then again, 4 over 14 is the probability for temperature to be hot. Then 6 over 14 is the probability for temperature to be mild. So now we do the conditional probabilities. Out of the 4 records where temperature is cool, out of these 4 records, we have 1 no and 3 yes. So that's going to be 1 over 4 and 3 over 4 for S. Then out of the 4 records where temperature is hot, we have 2 no's and 2 S. So that's going to be 2 over 4 and 2 over 4. Then out of the 6 records where temperature is mild, we have 2 no's and 4 S. So it's going to be 2 over 6. 2 of the 6 mild records have no as a class, and 4 of the 6 mild records have S as the class. So that's the conditional probabilities. And we're done for temperature. So the next thing is humidity. And if you sort the records based on humidity, we have 2 values, high and normal. So there are 7 high and 7 normal. So high and normal, 7 and 7. So 7 of the 14 absolute probabilities have humidity as high, and again 7 of the 14 has humidity as normal. Now the conditional probability cases, out of the 7 high humidity records, there are 4 no's and 3 yes. So you're going to have 4 no's and 3 yes. Then out of the 7 normal records for humidity, you have 1 no and 6 yes. So it's going to be 1 out of 7 no and 6 out of 7 yes. We're done for humidity. So now we'll do windy. So if we sort the records based on windy, we're going to have true and false as the 2 values. Let's go with false and true as they occur here. And we have 3, 5, 8 false records and 6 true records. So 8 false and 6 true. So now you're ready to compute the absolute probabilities. So 8 out of the 14 is false for windy, and 6 out of the 14 is true for windy. So now of the 8 false records, you have 2 no's and 6 yes. So that's going to be 2 over 8 no's and 6 over 8 yes. Then out of the 6 true records, we have 3 no's and 3 yes. So we have 3 no's and 3 yes. So this is our conditional probabilities table. So now we are ready to run through a test case. The test case is the outlook is sunny, temperature is hot, humidity is high, windy is false. So for given this test case, we have to find out what's the probability for the person to play tennis equals S. And for the same given this test case, what's the probability for the person play tennis equals no. And whichever of the two probabilities is larger, we have to go with that as a predicted class. Okay. So we'll do that. So probability for the person to play tennis equals yes, given this test case, equals probability for the test case, given the person played tennis equals yes, times the probability for play tennis equals yes, divided by the probability for the test case. In the test cases, outlook is sunny, temperature is hot, and all these things. So, right, so test cases outlook equals sunny, temperature is hot, humidity is high, and windy equals false. So that's a combination. So we have to now so equals probability for these test case values to occur, given that the person played tennis equals yes, times probability of play tennis equals yes, unconditional probability for that, divided by probability of these feature values, the absolute probabilities. So we have to look into these tables now, the conditional probability tables. And so probability for play tennis equals yes. What is the probability for outlook to be sunny when the class is yes? So this is the F class, and the outlook is sunny is here. So the probability for that is 0.6. Equals 0.6 times temperature being hot when class is yes. So class is yes here. Temperature hot is this thing, so that's 0.5. Humidity is high when class is yes, class is S. Humidity is high is here, so that's going to be that 0.428571 times windy equals false, and class is yes. So class is yes, windy equals false is going to be 0.75. So those are the conditional probabilities times the unconditional probability for playing tennis equals yes. So among all the records over here, we have to find out how many have yes as they play tennis. That's the unconditional probability. So we'll simply sort by play tennis. Okay, we can remove this second. We don't need, we cannot sort it more than once. So we have here 5 no's and remaining 9 has to be an S. So we have 9 over 14 as the probability that play tennis equals yes. Out of the 14 records, 9 have yes. That's the unconditional probability to play tennis. Divided by the probability of outlook equals sunny times the probability of temperature equals hot times probability of humidity is high times probability of windy equals false. So these are the absolute probabilities for each of the feature values here. So probability for outlook equals sunny is this number 0.357143. Probability of temperature equals hot. The absolute probability is 0.285714. Humidity is high. The absolute probability is 0.5. Windy equals false. The absolute probability is going to be 0.571429. So we need to compute these to the math. So that's going to be 0.6 times 0.5 times this 0.428571 times 0.75 times 9 divided by 14 divided by 0.357143 divided by 0.285714 divided by 0.5 divided by 0.571429. It's going to be 2.1262. So this is the probability that given this test case, somebody will play tennis equals yes. So that's the probability, 2.1262. So now we have to repeat the same thing for given the test case, find the probability that play tennis classes no. So you can copy and paste this work and make the changes. So we want to find now for no for this test case. So there was yes for the play tennis, change it to no. So test case remains the same. That's very important to remember. So probability of each of those feature values given that play tennis equals no times probability of play tennis equals no. That's the absolute probability. So the absolute probability for play tennis equals no will be 5 over 14 because we saw 5 of the 14 records have no as the class. So that will be 5 over 14. Now, for these, we can go back to those conditional probability tables and pick up the numbers. So for class equals no, what's the probability for outlook to be sunny? So that's going to be, this is the no class. Remember the feature values is still the same, outlook is sunny. So for S we have 0.6, for no it's going to be 1 minus of that 0.6, which is 0.4. So we can actually take 1 minus of each of these 4 product probabilities and have them here. So it's going to be 1 minus 0.6 is 0.4, 1 minus 0.5 0.5, can cross check. Class no, which is this, temperature equals hot is going to be 0.5. Then humidity is high, 1 minus of this for class no. So that's going to be this 0.571428. So 0.571428. Then windy equals false for class no is 1 minus of this. It's going to be 0.25. 5 over 14. That's also like 1 minus 9 over 14. Probability of play tennis equals no. Now you see the denominator is going to remain the same because the test case is the same. So these independent absolute probabilities are still the same. So the product of those probabilities will still remain the same. So you just compute the value of this. 0.4 times 0.5 times 0.571428 times 0.25 times 5 over 14 divided by 0.357143 divided by 0.285714 divided by 0.5 divided by 0.571429. So at 0.35, the probability for a person not to play tennis given this test case. So the 2.127 and 0.35, 2.127 is larger. So we conclude the person play tennis equals yes. That's the class. Okay. Now we look at a third example, back to some biological data. So we have data on 1,000 patients and they were diagnosed to be either having flu or an allergy or some other disease using the symptoms that were observed from these people. And we will now use this data set to predict the type of disease any new patient will encounter based on the symptoms values. The symptoms are having a fever, sneezing, and runny nose. And each of these three features have an yes or no answer values. And so you can see here, the first thing is to understand this table that's given to us. So there are three diseases out here: flu, allergy, and anything other than these two. So, and you're given here a total column as well as a total row. So the total column here indicates for each disease type, what's the total observed. So flu, you have 500 in total. Allergy, you have a 300 in total, and other diseases, you have 200 in total. So the sum of these three column values equals 1,000, and we have 1,000 patients here. And then now for each of these symptoms, which are the features, they are also given the number of people who recorded an S or a no for the particular disease. So out of the 500 that had flu, 400 recorded S for fever, 100 recorded no for fever. That's how to interpret this table. Similarly, out of the 500 for flu, 350 reported an S for sneezing, 150 reported a no for sneezing. And then out of the 500 who had flu, 450 reported an S for runny nose, and 50 reported a no for runny nose. And you can notice the sum of the two feature values for each feature will add up to 500 here. So 400 plus 100 is 500, 350 plus 150 is 500, 450 plus 50 is 500. Okay. So next we'll do the same thing, try to understand it. So this is the main first thing as we should do as a data analyst, try to understand the given data set. So now for allergy, out of the 300 people who are reported to have allergy, for fever, 0 had fever, yes. So then 300, all the 300 who had allergy reported no for fever. And 150 of the 300 reported yes for sneezing, and 150 out of the 300 reported no for sneezing. Then out of the 300 who had allergy, 300 report yes for runny nose, and 0 reported no for runny nose. So it means all the 300 who had allergy had runny nose and no fever, basically. That's how to interpret the data set. And then 150, half of them have sneezing, and the other half did not have sneezing. Now, for other diseases, out of 200 people who reported other diseases, 100 reported yes for fever, 100 no for fever, 150 yes for sneezing, 50 no for sneezing, 50 yes for runny nose, and 150 no for runny nose. So now if you add up these feature values for fever, yes, if you add up these three rows, 400 plus 0 plus 100 is 500. So that means across all these diseases, what's the probability for a person to have fever is S, is 500 over this 1000. Similarly, for no, the sum of these is 500. So sum of these two again, S and no, 500 plus 500 is 1000. Similarly, for sneezing, the sum of the S values, 350 plus 150 plus 150 is 650. So out of the 1000 patients overall, across all the diseases, 650 reported sneezing as yes. And then the sum of these three is 350, which is instantly 1000 minus 650. So 350 reported sneezing as no out of the 1000 patients. Similarly, some of these numbers is 800. So 1000 out of the 1000 patients, 800 reported runny nose as yes. And some of these numbers is 200. So 200 reported runny nose as no. So that's the kind of the way to look at this table. And we can now go ahead and build the conditional probabilities if you want, and then run through a test case. So that's what we're going to do that. Uh, so the features here are fever, runny nose, and sneezing. So we'll start with fever. The fever values are S and no. And you had 400, no, not 400. This 500 overall had S and 500 overall had a no for fever. So the absolute probabilities is going to be 500 over 1000 had fever, irrespective of the disease, across all the diseases, is what it means. Similarly, 500 over 1000 had no for fever. So now we are ready to calculate the conditional probabilities depending on the type of disease. So we can have either flu or allergy or other as the thing. So out of the 500 who reported S for fever, 400 belong to flu. So we can say 400 or 500. Out of the 500 who had fever, 400 had flu. And 0 over 500 for allergy and 100 over 500 for other diseases. Similarly, out of the 500 who had fever overall, 100 had flu, 300 had allergy, and 100 had other disease out of the 500 who reported no for fever. So that's our kind of conditional probability table for fever as the feature. So now we'll do the same thing for sneezing. And the sneezing, S or no again of the feature values. So total sneezing yes is 650 and 350 as no. So the absolute probability is going to be out of the 1000, 650 had sneezing yes, and 350 of the 1000 had no for sneezing. So now we are ready to calculate the conditional probabilities for these three diseases. So out of the 650 who reported S for sneezing, 350 had flu. So 350 over 650 is a conditional probability. Then 150 reported allergy out of the 650. And another 150 reported allergy out of the 650. Then out of the 350 who reported no for sneezing overall, 150 had flu, 150 had allergy, so that's a fraction, and 150 had other diseases. 50 over 350. So 150 over 350 for flu, 150 over 350 for allergy, and 50 over 350 for other diseases. So let's do now for runny nose. So runny nose, again, we have S and no as the feature values. So we have 800 reported yes for runny nose and 200 reported no. So the absolute probabilities 800 over 100, 1000 runny nose as yes, 200 over 1000 runny nose as no. So now out of the 800 runny nose as yes, 450 reported as for flu. So it's going to be 450 for flu divided by 800, the total runny nose as yes. Then out of the 800 runny nose yes, you have 300 reported runny nose, reported allergy when they had runny nose as yes. So it's going to be 300 divided by 800. And then it's going to be out of 800 with runny nose as yes, 50 had other diseases. So it's 50 over 800. Then out of the 200 who had overall runny nose as no, 50 reported flu and 0 reported allergy. So it's going to be 0 over 200 and 150 reported other diseases out of the 200. So this is a conditional probability table for runny nose feature. So now we have to, we can do a test case. So let me save this. Okay, so the test case is also given here. Fever is yes, sneezing is no, and runny nose is yes. So you have to similarly so these are the feature values. So you have to now compute the probability for each of the three diseases, flu, allergy, or other. And whichever is larger, we say the person is predicted to have that disease. So let's do one by one. So the feature values are these. So probability for a person to have flu given this test case is probability for the test case values for the features given somebody has flu times probability someone has flu divided by probability of the test case. The test case being given here. So probability this combination given that someone has flu times probability someone has flu divided by this. Okay, so let's go back to the conditional probabilities table. So given that someone had flu and fever S, so flu and fever S is 0.8, sneezing no and flu is going to be 0.428571. And what's third one? Runny nose S and flu is going to be 0.5625 times probability of flu. So probability of flu in the given data set, out of the 1500 had flu. So 500 over 1000 is the probability unconditional or absolute probability for someone to have flu. Now the denominator are all going to be absolute probabilities. Probability of fever equals S times probability of sneezing equals no times probability of runny nose equals S. And that's given from our absolute probability values here. Fever equals S, absolute probability is 0.5. Sneezing equals no, absolute probability is 0.35. Runny nose equals yes, absolute probability is 0.8. That's the test case. Okay, so if you do this math, That's going to be 0.8 times 0.428571 times 0.5625 times 500 divided by 1000 divided by 0.5 divided by 0.35 divided by 0.8, 0.6888, something like that. So this is for flu. So we can do the same thing for allergy. Do the same thing for allergy. So this is multi-class classification actually using Bayes. Someone had allergy. Okay, so now we have to look at the allergy column for the conditional probabilities. And fever equals S and allergy is actually 0. And then sneezing is no and allergy is 0.428571. And runny nose equals yes and allergy is 0.375. And out of the 1000, how many had allergy is 300, the absolute probability. So that's going to be 300. And denominator is remaining the same because the test case has not changed. And since we have a 0 in this product, the whole thing will evaluate to 0. Okay. So given the test case, the probability it to be an allergy disease is 0. So now we do the other. So this is other. Okay, so let's go to the other column. So given other as the disease, fever equals S, the probability is 0.2. Sneezing equals no with other 0.142857. And runny nose has S with other 0.625, 0625. And out of the 1000 people, 200 reported other diseases overall. So denominator is going to be the same. So none of the values are 0, so you have to do the actual multiplication now. So 0.2 times 0.142857 times 0.0625 times 200 divided by 1000 divided by 0.5 divided by 0.35 divided by 0.8 is going to be 0.00255. So the probability for it to be other disease is actually very low. Let's check the numbers. Might have done some mistake. Let me check. Check. We went with other. Whereas yes, 100 or 500. Yeah, this should be 500. So my calculations are wrong here. 50 over 350. So that's the wrong thing. And 500 over using this no. 50 over 350. Then runny nose is yes, 500 over 850 over 800. So this should be what I have. Let me just cross check here. 100 over 500 times 50 over 350 times 50 over 800 times 200 over 1000 divided by 0.5 divided by 0.35 divided by 0.8. Yes, this should be 00255. Okay, so 0.00255, which is the same number I got in my calculations now. Previously, I had done some mistake in the slides, so I'll update it. So this is the right math that we did today. And so 0.00255 is very small compared to what we got for flu. What we got for flu is 0.6888. So let me fix, this should be the correct one. Let me go back and see here. Fever as yes for flu 400 over 500. Sneezing as no for flu is 150 over 350. And runny nose as yes is going to be 450 over 800. So that's going to be now 400 divided by 500 times 150 divided by 350 times 450 divided by 800 times 0.5 divided by 0.5 divided by 0.35 divided by 0.8. So 6888. This should be 0.6888. That's what we got here. Okay, so 0.6888. So still flu has the larger probability, and we kind of come to a final prediction that the person is more likely to have a flu compared to it being an allergy or any other disease with this test case. Okay. So we'll stop temporarily. Let me take a break.